Okay, time to get started. So, as you've noticed, no quiz today. At least no quiz on any sort of pre-lecture material. There was one pre-lecture to watch. I hope everybody watched that. But going forward from today on, there will still be quizzes, but those quizzes are there just to check attendance. It's kind of a little hack. I mean, I can't realistically call names and check attendance that way, right? So the way attendance is going to work going forward is every day on the board there's going to be a number written down here. That number is the answer to the quiz. So at some point during the lecture, anytime during the lecture, although only during the lecture, go to Sakai, tap on the quiz, titled by today's date, enter that number, and you're done. Now, probably a healthy thing to do while you're in there, while you're in Sakai, after you enter the quiz, go ahead and whip over to the grade book real quick and make sure that the score recorded correctly, just in case, right? Sometimes students might forget to hit the submit button, or you might inadvertently typo. Right? Happens to the best of us. If you do inadvertently typo and have the wrong answer entered, no problem. You can answer that quiz questions as many times as you like. It will record your highest score. So if you were right the first time, then went in and changed it and got it all wrong, you're good. Right? Anyway, the point is you can tell all this by going into the grade book and confirming that the point is there. Okay. So might as well do it now, I suppose, but certainly sometime before the lecture's over, please go and do that. So one other thing I wanted to mention. Does anybody have a question or something? Did it not work? Is everybody good? Okay. So one other thing I should mention, we are starting with recordings of live lectures. So starting today and going forward, this is all being recorded. So what is being recorded, just so you know, is the screen, well, to be precise, my laptop screen, and then audio. So the thing is, it's picking up my voice primarily. However, you are in the room. If you ask a question, for example, your voice might get picked up on the recording. I'm not saying this because I think anyone cares. This is just an FYI because it is going up to YouTube, right? And if you don't want to be on YouTube, then it's something to keep in mind. Okay. All right. Right. So let's see here. I think I have all of this covered already. One other thing I'll mention about the availability. I put a 5-minute grace period on either side of the lecture. So these quizzes will actually open up 5 minutes before lecture starts. So if, for example, you'd like to just get this out of the way so you don't have to think about it during lecture, great. It'll be open at 5 minutes before the start time. Also, if you, for whatever reason, maybe you come in a couple minutes late, you don't have time, and you don't want to be distracted during the lecture, 5 minutes after the lecture is over, the quiz is still open, and you can still enter the score then. But you do have to enter the code, the answer to the quiz, sometime while it is open, from 5 minutes before class starts to 5 minutes after class ends. Okay, are there any questions about any of this going forward? I guess maybe one final reminder, do recall that attendance does count as part of your grade. You can see the details on that on the website, right? There's a web page dedicated to talking about grades. So it's a small portion of your grade, but it is there. All right, keep that in mind. All right. So I want to start talking about some of the material that was in the pre-lectures. Just going to do one example. It's an old test question, as we often do. And so this pertains to this material about gain and phase shift, and there's all this discussion back here about how to compute gain and phase shift. And there's, the big idea, recall, is that we handle this differential equation by looking instead at this differential equation. This one is the complex, kind of the associated complex equation, and algebraically it just happens to be easier. It is definitely easier because it doesn't involve both sines and cosines. The algebra of exponentials is nicer than the algebra of trig. It's just a nicer equation. Once you solve that, of course, then you make real and imaginary arguments, right? If you know how to do this, then looking at the real part solves that differential equation. Looking at the imaginary part solves that differential equation. So that's the big idea. You can then translate that down into, solving for your gain and solving for your phase shift. And that's a nice application. This old exam question doesn't really get around to talking about the gain and phase shift part. This is just understanding how the solution to a complex differential equation helps you then subsequently find the solutions to two corresponding real differential equations. So, first part of the question says solve that differential equation, and you'll note that this is it's practically straight out of section 4.3. In fact, this question, if I remember correctly, is the question that I had on the list of lecture materials for 4.3. And I skipped over it because, I didn't want to deal with the complex valued equation. I wanted to give you all a chance to digest that first in yesterday's pre-lecture. But ultimately, it's pretty similar stuff. We're going to look at the right-hand side, and our guess comes from just looking at the right-hand side, looking at the form of the right-hand side, introducing a fudge factor. Here we're calling it T, but we could have called it like A or whatever, like we did back in section 4.3. And then taking your guess, plug it into the differential equation, and solve for your fudge factor. Right? So here it is. The one little twist in here. Now you do have to take some derivatives. It's just the derivatives of exponentials. That's easy. Right? That's kind of the point. Cancel the exponentials. Solve for t. Okay, one little complex arithmetic thing that, yes, we do have to do is that we have to do a complex division. But that's not that bad, right? That's a relatively easy little bit. And once you know this t, then this guess that we've made becomes that. Don't forget that extra factor of 7 up there that we left in there on purpose. And then the last detail is to figure out how to take this complex valued solution and write it as in a real part and an imaginary part. The way to look at this, my opinion, is to see that we have a product of two complex numbers here. Don't make the mistake of trying to interpret this too creatively. This is a complex factor. This is a complex factor. We have to multiply complex times complex. You can do that in any of several different ways. I think the easiest one here is to put both of these complex numbers into rectangular form. So you'll notice that's all I did in going over this next line, is I took that polar form for that factor and I rewrote it in rectangular form. And now it's just a matter of cranking it out. I mean, now I have rectangular times rectangular. So let's see here. Real times real gives me real. Imaginary times imaginary gives me real. Don't forget I squared is -1. And then likewise for the imaginary part, real times imaginary, imaginary times real. Details. So let me take a pause on this first part of the problem. Does anybody have any questions so far? Does everyone see how this is really? I mean, we kind of could have done this on our day that we were talking about section 4.3. It's not that different. Okay. Having done this, we get free solutions to a couple of differential equations. So this equation, you notice, is exactly the real part of the equation above, as observed there. And so therefore, this function that we're trying to solve for there, that u, is just the real part of the above solution, and that real part is that. Likewise, this equation here, that's just the imaginary part of the equation that we were solving in the previous part. So we look at the imaginary part of the solution, and that's this right here. So two free solutions from having solved one differential equation. Any questions about this? Is everybody good? Yes?
Just to clarify, you know that it's the real with the imaginary part because the cosine part only corresponds to the real.
Yeah. Well, I mean, yes, but I mean, there's no need to make a sort of a general rule out of that. I mean, we can just look at and observe that this is literally the real portion of that function. Yeah, it just is, and therefore we proceed. Yep. Anybody else? All right. Okay, so moving along. Whoops, where am I? Oh, yeah. Okay, right. Okay, so moving on to chapter 5. So let me just remind you momentarily, sort of where we are in the big scheme of things in the course. We started off in this course doing a bunch of linear algebra. Systems of linear equations, reduced echelon form, pivots. Then we talked about, matrix multiplication and some cool things you can do with that. Determinants, linear independence and span, generalized it to a broader notion of vector spaces, and from there, other things. Then we took an aside, and we've spent the last, a couple of weeks, or so, talking about differential equations, right? So this course is about linear algebra and differential equations. So we've done now a little bit of linear algebra and a little bit of differential equations. Where we are going now is back into linear algebra. So chapter 5, after which we're going up to chapter 9, all of that is linear algebra. So more linear algebra. After which we will then go back into chapter 6 and do more differential equations. So there's kind of 4 parts. Linear algebra, then differential equations, then linear algebra, then differential equations. Now, the reason, just so you know, why do we kind of bounce around like this? We do the linear algebra necessary to solve the kinds of differential equations that we're going to be faced with, namely all this chapter 4 differential equations. We needed ideas like independence and span, bases, dimension, right? We needed all that stuff to be able to do those differential equations, reasonably appropriately. Likewise with this next bit of linear algebra, we're going to be doing a bunch of linear algebra here that is the linear algebra necessary to solve another large collection of types of differential equations. And let's not talk about what those differential equations are just yet, but anyway, that is coming, right? So all this linear algebra that we're doing now is part of that story, part of what we're going to need to be able to solve the differential equations in chapter 6. Okay, first thing I want to define is something called a linear transformation. And sigh of relief from me, because I keep wanting to use the word linear transformation as we've gone through this course. We've actually seen a bunch of linear transformations already, and I haven't used the word because, the book doesn't define the word until chapter 5, right? So I've been having to bite my tongue and say, this function is linear, and things like that. So of course, you'll notice we've used the word linear quite a bit. Okay, so we're going to get around to defining linear transformations in today's lecture, finally. First, a little terminology about functions, just so we're all on the same page. Functions have something that's called a domain. This is where you get the things that go into the function. Okay. Functions also have something called a target. The target is where the outputs from the function go. So domain and target are the fundamental sets that we associate to a function. This is where the inputs come from. This is where the outputs go to. Okay? All it is. And mind the notation. So when you're talking about a function is very often students think of a function as being a formula. It's not really quite the whole story. A function is actually a trio, and the notation that we often use indicate what is the function. That's typically where you think of the formula that does the calculations of the output values. But then also, what is the domain over which it's defined? And you've got some flexibility there. You don't have to define your function over all the input points where it could be defined, right? So that's part of the definition of the function. And then likewise, what is the target? So you should think of a function as being this trio of things. Domain and target, and then formula for how to get there. Okay. How we doing? Everybody on board so far? There are some other names that you can use, by the way. Sometimes people like to call the target the codomain. It's fine, I suppose. Some people like to call it the range. This one I'm not comfortable with for reasons that I'll explain in a minute. But anyway, I have seen in some books the word range used to mean target. I'll complain about that in a minute. Okay, now, to complicate things a little bit, here is another set that you can associate to a function. This next item that we're going to talk about is not really one of the fundamental parts of a function. A function is a named formula combined with a domain and combined with a target. That's what a function really is. This other thing is called the image, and it's the set of actual output values. Right, so in other words, if you look at all of the inputs in the domain, plug them all into the function, look at all of the things that come out, that complete set of outputs I would call the image. Notice, the image and the target are not the same set, necessarily. It might be. But you can see the way I've got this drawn figuratively here, that it need not be. I mean, just because all the points in the image, namely all the actual outputs, just because they're required to be in the target, that doesn't mean they're actually going to fill up the target. There could easily be points in the target that just don't get hit at all. Right? So these two sets are not the same thing. The image is a different concept. It's a different thing, really, than the target. And between the two of them, the target is really the more important one. Okay, so a couple of examples. And let me make a little terminological reference then. Here's why I don't like the term range. And that is, I have seen the term range used as an alternative for target, and in different contexts, I've seen it used as an alternative for image. That's really confusing, right? The same word in different contexts I've seen it used referring to two different things. Two things that are importantly different. So just to avoid the resulting confusion, I try to never use the word range. And I kind of encourage you likewise to let's just not use the word range in this class. I think target is unambiguous, and I think image is unambiguous as well. Okay, so examples. Here's an easy one. Look at this function from R1 to R1, defined by f of x is equal to x squared. Now keep in mind, we're accustomed to thinking of a function as just being a formula. That's not what we're doing here. We're thinking of this function as being a trio. That formula combined with that understood to be the domain and that understood to be the target. Okay. All right. What's the image in this case? What are the actual outputs? What actually comes out of this formula is non-negative numbers. In fact, every non-negative number does in fact actually come out of this formula. But only non-negative numbers come out of this formula, right? So the target is all of R1, and that is not the same as the image here. All right. Reasonable question to ask. Who needs, what's the purpose of even having a target? How about this? How about let's throw away the concept of the target. Who needs all that slack around, the image is the actual outputs. That's what I need to keep track of, isn't it? So why allow the target to be this uselessly larger thing, it would seem. So here's my answer to that question. Sometimes it's really hard to see what the image is, but really easy to see what to choose as a convenient choice of target. So let's suppose that for whatever reason you're interested in a formula like that, and that's not the craziest thing in the world. It's just a polynomial. That's a quartic. That's a little weird, but hey, the real world is full of all sorts of inconvenient, bulky things to have to deal with. For example, this. Well, it's really nice to be able to say, look, this is a function from R2 to R1. R2 being the domain because, well, there are two input numbers that go in. Everything that goes into this function can think of it as a vector in R2. And what comes out, great big ugly formula, sure, but what comes out is always a real number. And that's easy to say, right? I mean, look at that formula and say, okay, well, I don't know which real numbers are coming out of this, but they're always real numbers. So that's easy. On the other hand, what's the image of this function? And I have to admit, I don't know. Clearly the output values here can get arbitrarily large because I have positive coefficients on the high powers of x and y, right? So I can get as big as you want, but I can't get as small as you want. What is the minimum value here? That's a hard question, right? In fact, if you wanted to find that minimum value, well, you flash back to Math 212, you take the gradient, you set it equal to 0, and observe the gradient here is a cubic, right? Both coordinates of the gradient are cubic, so you have a system of cubic equations. That's a really, really hard problem. So maybe I just don't have any use for that image. Maybe I don't need to know the actual outputs. Maybe all I really need here is, look what kinds of things are coming out here. Is this function spitting out real numbers? Great, cool, that's all I need to know. I need to know if it's spitting out matrices or numbers or, fundamentally, issues of type. I need to know what these things are, but I don't need to know precisely exactly the image. So it's a very convenient thing to think of a function as in terms of domain and target and not image. Okay. All right. A couple of comments about lingo. Oh, excuse me. I'm sorry. Getting ahead of myself. Making a definition. Now that we have our terminology about functions straightened out, here's our definition. I'm going to define something called a linear transformation. Linear transformation is this function here. And there are three requirements. First requirement, the domain has to be a vector space. Second requirement, the target has to be a vector space. And the third requirement is the function has to satisfy this condition that we call the linearity condition. Of course, you recognize this condition. We've already kind of done a bunch of stuff with this condition. We've talked about formulas that are, functions that are linear. We've talked about linear differential equations. We've talked about the linearity of determinant, one row at a time, multilinearity, various other places. So those are the requirements. Any function that has a domain that's a vector space, targets a vector space, and the function satisfies the linearity condition for all vectors in the domain and all real numbers as coefficients. Linear transformation. Okay. All right, so we've seen a bunch of examples of linear transformations so far. Okay, some alternative ways to write this down. And by the way, pick up a different linear algebra textbook. You might see these as the definitions of the linearity condition. This condition here is actually equivalent to this condition here. So, doesn't seem immediately obvious, but if a function has the feature that a linear combination of two vectors before the function or after you apply the function, same thing, makes no difference. If the function plays nice with linear combinations of pairs of vectors, turns out it also plays nice with linear combinations of any finite number of vectors. That's not terribly hard to prove. You can play with that if you'd like. If you have any questions about how to prove this, you can ask me in office hours, ask your TA in discussion section. Turns out, anyway, they are equivalent. And then here's another equivalent formulation. And again, pick up a different linear algebra textbook. You might see this as the definition. The function plays nice with vector addition and simultaneously must also play nice with scalar multiplication. So any function that satisfies this pair of conditions also satisfies both of the above, and likewise vice versa. Okay. Any questions about that? Take your pick as to which ones you want to apply. Sometimes in certain situations, it's really nice to know that this is true. It's really nice to use this condition here. On the other hand, it's kind of easier to prove things with that condition because there's only two vectors, and it's easier to work with. And sometimes you might find it easier to prove things with this pair of conditions because even though there are, in fact, two of them, each one individually is maybe a little easier looking, maybe a little bit less sort of scary. So take your preference. But I'm going to use this one here as the definition. How are we doing? Is everybody happy? Questions? All right. Okay, I've already used this term, but this is very common lingo to say that a linear transformation commutes with linear combinations. Let's talk about this word commutes for a moment. I hope you all remember what it means for an operation to commute. So, for example, addition is commutative. When I was in elementary school, they made us learn these words. What does it mean for an operation to be commutative? What does it mean for an operation to be associative, etc.? I have no idea why they were making me learn this. Still not 100% clear on that, because every operation that we were dealing with at that stage, all the operations had all the properties, and so it seemed weird to give them such big names. So the idea of commutative, though, is that if you do them in this order or you do them in that order, it doesn't matter, you get the same thing. A plus B equals B plus A. So there's something that's at least cosmetically kind of like that in these definitions. So to say that, this function commutes with linear combinations, what we're saying is, and it's a slight abuse of the term, we're saying you could do a linear combination and then apply the function, or you can apply the function to the vectors individually first and then take the linear combination and you get the same thing. So it's got a little bit of this same kind of a feel to it. It's different, a little bit different, of course. But the lingo is very common. You'll hear people talk about this all the time. A linear transformation commutes with linear combinations. It's I think, actually a pretty elegant way to say what it is that this is. Okay. Similarly, of course, commutes with addition, commutes with scalar multiplication. Commutes with addition is that. Commutes with scalar multiplication is this. Okay. All right. Okay, so now a little bit of lingo. Sometimes in your situation, there's a function involved. And the function is a linear transformation. And yet, sometimes in that situation, it might just be a little bit inconvenient to say such and such is a function, and this function satisfies the linearity condition, and therefore is a linear transformation. That's just a lot of words to say, and you might not want to actually say all that or write all that down. And so people have developed little shorthand ways of talking. So for example, it's a very common thing to say, a matrix acts linearly on vectors by left multiplication. Or in fact, even a little bit shorter, you might say matrices act linearly on vectors. And it's understood. You know, if you have a matrix and a vector, what do you do with them? Well, you multiply. Right? So when you say A acts linearly, what that's saying is that there is a function involved in this process. The function is, you give me a vector x. Here, let me highlight. You give me a vector, and I'm going to apply a function. The function is the act of multiplication, and this function can be thought of as a linear transformation. But isn't it just easier to say it acts linearly on vectors? A matrix acts linearly on vectors. Okay, so be prepared to interpret in this way. When you see the word linearly, let me highlight here. When you see this word linearly, that's your cue to realize, okay, we're describing here something that is a function. For whatever reason, the speaker has chosen to not bother actually saying the words, and here I define the following function. But they're describing a certain function, so look at your situation and ask yourself, what are they talking about? What is the function in play that they're describing? And then realize that when they say linearly, they're just saying that function is a linear transformation. So now you'll probably recognize that we've already defined the function that does this. We've already talked about this thing, t of x is ax. Right, we made the observation back in chapter 1 that if you give me a matrix, then I have all that I need to define a function per this formula. A function is something that, when you give me an input, let's say x, then I can give you the output. The formula for my output is ax. So we've already talked about that as a function. That is the function being discussed here. All this is saying, A acts linearly, is when you take a matrix A and reinterpret it as a function, perhaps called t, then that function t is a linear transformation. Anyway, heads up on the terminology. A few more examples. Same kind of thing. A different context, different functions to talk about, but same sort of terminological shorthand. If you have a plane, let's say a plane P, right? And if you have if you think about projecting points, so you've got some point X there, and the projection just identifies, what is this point over here? That's the point in the plane closest to the original point X. Here's a function. Right? You give me an X, I give you a point inside of this plane that has this feature. Right? You give me any X, there is a corresponding nearest point in the plane P. Okay. How do people talk? This is sometimes referred to as a linear map. Or sometimes people say the projection into a plane is linear. All right, well, they didn't say the word function, and they didn't say this function is a linear transformation. But again, that's a lot more syllables, and it's a lot easier to, if you just say, look, here's a projection. clearly that's the action that we're describing. That action we can think of as a function. You can interpret from the context on your own. What is the domain for this function? What's the target of this function? And having all that identified, I'm just making the observation that function is a linear transformation. Okay. All right, so again, you're going to hear this kind of thing. By the way, the reason that I'm talking about these examples is because Math 353 instructors have told me that this is something that they find sort of surprising, that they'll make comments like this, say, the projection is linear, and students say, I don't know what you're talking about. What does it mean for a projection to be linear? All I know is, I know what a linear transformation is. What are you talking about here? Right? And so students weren't making the connection about the lingo, right? So I just want to point out, just be on the lookout to interpret appropriately in context, like these examples. Two more quick examples. We described this as a linear operator, right? Well, I guess I haven't used that notation yet, but the idea of taking a function and doing to it as follows, taking that function and replacing it with its second derivative minus e to the x f prime of x. Right? That's a linear function. We've written this in the past as L of f. And we've talked about L back in chapter 4 as being linear. It takes in a function, and by way of a formula like this, you get an output. So we've thought of this as a new kind of function, and it is a linear thing. And we call it an operator because it's a function that takes in other functions. It's a differential operator because it involves taking certain derivatives. Right, so we've described this thing here as a linear differential operator. We've thought of it as a function, and now I'm just introducing the idea that it's a linear transformation. But again, I might not want to actually go to the trouble of saying all those words. If somebody says this thing here is a linear operator, they're just drawing your attention to the linearity of this process, the linearity of this function, which you should infer is a linear transformation. Okay. Here's an example that goes way back. One of the first things that we talked about in the course. This thing here we described as a linear system of equations. Well, there's that word again, linear. Right now, why do we call this a linear system of equations? How do I interpret the word linear in this context? Well, linear is telling me two things. On the one hand, it's telling me there's a function involved in this story that we're considering. And here's that function. You give me inputs x1 through xn. I plug in on the left side of the equation and produce this output. Which I will call here t of x. The input having been x. Okay. You might even recognize that this thing here, this t of x, is just a times x. It's the same a times x that we used back in chapter 1. And so really this is just this first example all over again. This example, same thing, just kind of interpreted in a different context. This is the function. The use of the word linear there is to say, okay, in this situation, in the function that we're clearly talking about here, that function is a linear transformation. Okay. Everybody good? Questions? Okay. All right. So heads up. Whenever you hear this word linear, find the function. Interpret it as a linear transformation. Okay. Okay, let's get our hands dirty here. This is everybody's got to go through and do one of these in their lives. Y'all are probably going to do a handful, a few. But this is an easy function, and we're going to directly confirm that this function from R2 to R2 is a linear transformation. Just brute force, we're going to directly confirm, directly from the definition. A couple of easy, obvious checks. The domain, all ordered pairs, that is clearly a vector space. Right? The target, well, what comes out is an ordered pair, namely a vector in R2, also clearly a vector space. Right. So, the main thing that has to be checked here is, does this function satisfy the linearity property? Here's what we're going to have to do. We're going to have to plug in and confirm that when you put a linear combination in, then you get the appropriate expected linear combination out. And this is just a brute force plug and chug, and I think we should go through this just to make sure everybody sees how we're explicitly doing it. And that's all that's going on here. Okay, so here we go. Starting up here. Okay, this input. What am I going to do with this input linear combination vector? Notice in order to be able to evaluate the function, I'm going to need to know the two individual coordinates. I'm going to need to know the first and second coordinates. So I'd better give names to the coordinates of that first vector, x1. I'm going to call its coordinates x1 and y1. And this second vector, x2, call its coordinates x2 and y2. That's just given names, right? Which I need to do again so I can plug into the function. Okay, now before I plug in though, I'm going to need to know what is the first coordinate of this whole thing. So I've got to multiply out and combine, my input here. And this is just a Math 212 thing, right? The way you multiply vectors, the way you add vectors, old news. And now notice I have what I need. I can see right here now that is what's going to go in as my x. That is my first coordinate of my input vector. And likewise this thing here, that is my second coordinate of my input vector. And now it's just a matter of plugging in. Let's see here, that x goes there and there. That y goes there and there, plugging in for what they are. There's the y's, there's the x's. So that's just, I haven't really done anything. I'm just plugging in. This is my first coordinate, this is my second coordinate, plugging into t, this is what comes out. Everybody on board? Questions? Everybody's happy? Okay, what do I do then with this thing I've got down here? I need to show that this thing is a t of x1 plus b t of x2. How am I going to show that that thing is equal to that thing? This is just a matter of moving things around. Strategically, notice this factor of a here. That's only on the sort of the first term, right? There's no a's over there. So all the terms over here that have a's in them, I should kind of move over here over to the left. Right? And then likewise, let's look at the b here. That b, that's only on the right term. There's no b's over here on that left term. So I need to find all the terms that have b's in them and sort of move them over to the right. That's just shuffling things around. Again, nothing really happened there. Having done that, not hard to see that you can factor out common factor of a out of all these terms. Likewise, the b's on the other terms separate into two separate terms. Observe that that's exactly equal to that. That's the definition of t. That's exactly equal to that. That's the definition of t. And yay, we're done. Right, it worked. So the brute force checking of linearity is just slowly and calmly plugging in and moving things around to confirm that what is supposed to be true is true. All right. Everybody good? Okay. All right. Sadly, not everything is a linear transformation. Here's one that isn't. So here I have a function from a vector space R2 into a vector space R1. Here's my formula. I'm using the letter T, just like I did in the previous example. Right? It seems I might even be trying to sort of implicitly suggest that this is a linear transformation, but let's check and see if it actually is. And it just isn't. This fails the linearity condition. Easy arithmetic. Plug in 2, 0, you get 4. Plug in 1, 0, you get 1. So 2 times that gives you 2. If this were a linear transformation, these things should be equal. Right? By linearity. They aren't equal. They should be, they aren't, we're done. This is not a linear transformation because it doesn't satisfy the rules. Everybody happy? Quick observation about, let's say, our obligations here. How come I could just do an example here, whereas on the previous page I had to actually crank out a whole thing with algebra? And the reason why is it's a lot easier to prove that something is false. Let me rephrase that. It's easier to prove that something is not always true than it is to prove that something is always true. If you want to prove that something is not always true, all you have to do is find a counterexample. So, no need for me to consider other cases where T may or may not do what it's supposed to do. It does not always satisfy the linearity condition. I have a counterexample, and that's all I need. Right? A counterexample, an example over here. If I were to, somehow or another, maybe I just, looking at this, if I just say, yeah, it's linear because. Look, for example, what if x is 1, 0? What if, what if the first vector is 1, 0? What if the second vector is 2, 5? And plug in and confirm that it works for that one case. Doesn't really prove anything. Proving that something is a linear transformation requires showing that that is always true. One example of it being true does not show that it works in all the others. So you have to do some algebra to prove that something is. Quick counterexamples are good enough to show something isn't. What do y'all think about that? Is everybody happy with that observation? Okay. All right. Okay. Here's some other interesting linear transformations. This first one is a little bit of a brain stretch. Let's see here. Oh, come to think of it, we're not going to have time to finish this. You know what? Let's not get into this today. Let's draw the line right here for today. We will pick up there on Wednesday. See you later. Have a good one.